Welcome back. Let's learn some new concepts. So today we are going to be adding 6 new concepts onto your physics everything sheet. You can add these directly below efficiency on page 2, and it might go into page 3. That's great. So feel free to just keep going in order. Okay, so concept number 1 is horizontal velocity. So horizontal velocity, we're going to represent with v sub h, right? V for velocity, and then the subscript h for horizontal. And horizontal velocity is the average speed on a flat surface with no outside forces. So what that means is the object is moving sideways and nothing is pushing back against it, so it's a constant horizontal velocity, no forces of friction, anything like that. The equation that we're going to use is v sub h is equal to d sub h over t. This is looking really familiar, right? Velocity is distance over time, or horizontal velocity is horizontal distance over time. Basically, we're just re-emphasizing that we have to separate horizontal from vertical as we note, or as we calculate. The unit is meters per second. And then a note for this one is that horizontal velocity is constant, assuming no outside forces. So those outside forces would be things like friction. Acceleration due to gravity will not play in because that's vertical, right? Horizontal doesn't include the vertical components. Those are independent of each other. All right, our second new concept is vertical velocity. Vertical velocity, or v sub v, is going to be represented with a lowercase v and then a subscript v. It's going to be defined as the velocity of a falling object going up or down. So up or down, it's still an object in free fall, right? Free fall meaning nothing's touching it. It's up in the air. Even if it's still going up, it's technically in free fall. The vertical velocity is equal to the acceleration due to gravity times the time of the fall. So the vertical velocity is the acceleration due to gravity times the falling time, or VV equals A sub GT, right? V equals AT. That's a manipulation of the acceleration equation, A equals V over T, and then we just move some stuff around. Okay, but this is the falling time, acceleration due to gravity, and vertical velocity. The unit, because it's a velocity or a speed, is still meters per second. And the vertical velocity is always changing because it's constantly being accelerated downwards. So if the object's going up, it's slowing down going up, getting less vertical velocity. If the object's going down, it's speeding up going down. So its vertical velocity is increasing in a downwards direction. All right. The third concept we're going to add is vertical distance, or d sub v. D for distance or displacement, v for vertical. That is the distance fallen by an object that's starting initially at rest. Okay? So if I'm starting from an initial rest, then I can use this equation. And that equation is that the vertical distance is equal to 1/2 the acceleration due to gravity times the time squared. Now, if we have an initial vertical velocity, then I could add in this little bonus piece, which is that distance vertical is equal to the initial velocity, or v sub 0, velocity at time 0, times the time that it's going, that initial velocity, plus 1/2 AT squared. So this is just another version of this equation, but I would stick with the big black one in most cases, unless we happen to have an initial velocity vertically, which is going to be very, very rare for our class. Just stick with this guy. Yeah. It's a distance, so the unit is in meters, and really nothing to know about vertical distance. It's how high. I guess we could also say that a note is that it is also called height. So height is equal to vertical distance. Just different word. All right, now 2 new concepts, and these are totally new concepts. The first one is momentum, and the second one is impulse. So let's start with momentum. Momentum is represented by the variable lowercase p. I gotta be honest, I have no idea why we would use lowercase p to represent momentum. There is no p in momentum. It's not even like the next letter, LMNOP. We skipped N and O to get to P, I don't know. But we use lowercase p for momentum. And momentum, in the least sciencey words I can use, momentum is the amount of oomph an object has. Thought of another way, this is like how difficult would this object be to stop, right? Could you stop it easily, or would it take a lot of effort to stop it? That's kind of the amount of momentum that it has. So for example, a really large object moving really fast, like a bus, would have a lot of momentum. It's really hard to stop. A very light object, like this pen, moving relatively slowly, has very little momentum. It is easy to stop, right? I can stop it just like that. A bus, big mass, big velocity, very difficult to stop, lots of momentum. All right, so our equation is that P, or momentum, is equal to the mass times the velocity. Okay, so the momentum of an object is equal to mass times velocity, or I could also phrase it as mv equals ft, or m delta v, m change in velocity, mass times the change in velocity is equal to the force times the change in time, and this equation will become more relevant in just a second. Momentum is equal to impulse. So the units there are kilograms times meters over seconds. That's equivalent to newtons times seconds, but I got that by saying the mass equation, the mass unit was kilograms, the velocity unit was meters per second, so I just squish them together and I get kilograms meters per second. All right, so one note is that momentum is equal to impulse. Specifically, the change of momentum is equal to the impulse given to an object. And as we're going to find out right now, impulse is the amount of shove given to an object. So if I have an object and I give it a shove, I've given it an impulse. Shove is probably a bad, not scientific word either, but it explains what's actually happening. So the amount of push I give it then gives it a certain amount of oomph and makes it however difficult to stop. So the impulse is then the change of momentum. Impulse is represented by capital J. You might be saying, wait, we already used capital J. Capital J was joules, which was the unit of energy. That's true. That's when it's a unit. When it's a variable, it stands for impulse because of all the J's in the word impulse, obviously. I got no idea. No idea why J would be impulse. So it's the amount of shove. Impulse is equal to the force times the change of time, or the amount of time that you are pushing the object, right? How long is the impulse occurring for, times the force exerted during that impulse. The other equation that we gave above is that mass times the change of velocity is equal to force times the change in time. Basically, this mass times change in velocity is the momentum. This is the impulse. So the oomph is equal to the shove. The momentum is equal to the impulse. Change of momentum equals impulse, or impulse equals change of momentum. The unit, well, since impulse is force times time, that would be newtons times seconds. But since impulse equals momentum, newtons times seconds is also equivalent to kilograms meters per second. And we know that impulse equals momentum. All right, last thing to know for momentum is this concept of conservation of momentum. So there's no variable for conservation of momentum. It's just the idea that momentum is always conserved. What does that mean? It means that the momentum before a collision is going to be the same as the momentum after a collision. And that would be the total momentum in a closed system. So if I have two objects, one object standing still, the other object comes in, the total amount of momentum before has to equal, after they collide, the total amount of momentum after. So in this case, one object came in, one object was stopped, boom, second object stopped, other object kept going. The momentum before the collision has to equal the momentum after. What if they're both moving? Boom, they could crash off each other, and the momentum before equals the momentum after. What if they stick together and hold? Then the momentum before has to equal the momentum after. In every case, momentum before has to equal momentum after. So, is there an equation that we could use? There is. It looks like a really complex, tricky one, but it's basically just taking the momentum of the first object plus the momentum of the second object before the collision, and then setting it equal to the momentum of the first object and the momentum of the second object after the collision. So what I've done is I've used red for initial and final. Initial means before the collision. Final means after the collision. The collision would be taking place right in the equals sign, right there, right? So right here is the collision, okay? So before the collision, object 1 is M1I, V1I, object 1. Object 2, M2I, V2I. I stands for initial, 2 for object 2. After the mass and velocity of the first object afterwards, plus the mass and the velocity of the second object afterwards, are equal to the total starting momentum. So this is the total beginning momentum. This is the total ending momentum. They have to end up equal to each other. Cool. If they end up sticking together, then they would add the two masses together and they'd have the same final velocity. So that number and that number could be the same. If they don't stick together, if they bounce off each other, then they could have different final velocities. And so this equation works in every case. So it's a really helpful one. All right. So that is our physics everything sheet for momentum, impulse, horizontal, vertical velocity, and vertical distance. All right. Good job adding those to your physics everything sheet so that now you will be ready to use those in future problems. Enjoy.